Check it.
Okay, welcome back. Today we're going to talk about lesson 6-7, day 1, Descartes' rule of signs. Now, what Descartes' rule of signs, it sounds kind of fancy. It's actually just a really simple way to figure out how many of your real roots are positive and how many of them are negative. Okay, we know from the fundamental theorem of algebra, the FTOA as I like to call it, okay, that whatever the power of your function is, the degree of your function, that's how many roots you're going to have in total. So this is a fifth power function we have here in the example, fifth power. That means that all of our roots, whether they're real or imaginary, have to add up to 5. So you can have 5 real and no imaginary, for instance, or you can have 3 real and 2 imaginary, or you can have 1 real and 4 imaginary. And the reason why I'm going down by 2s is that imaginaries have to come in pairs. There's no such thing as 1 imaginary. This is not possible. 1 imaginary, that would give you 4 here. This in the red is not possible. Same thing with, you can't have 2 real and 3 imaginary, because you can't have an odd number of imaginaries. That's also not possible. They all add up to 5. But only the ones where the imaginary numbers are even numbers is possible. So this is not possible, this is not possible. Okay, but now within the reals that we do have, how many of these are positive reals and how many of them are negative? Here's what I mean. If you're looking at a graph, if you're on this side of the y-axis, you're positive. Positive x's, positive roots. And if you're on this side of the y-axis, you're negative roots. So how many of, let's say I had 5 real roots, and maybe, I don't know, I had 1, 2, 3 of them were on this side of the graph, and 2 of them were on this side, right? So I can tell what you're positive and what you're negative using this Descartes rule of signs. And when you see how it works, it's actually really simple. So let's get into it. Okay, Descartes' rule of signs basically lets you know how many possible positive roots you have, real positive roots, by just looking at how many sign changes there are from term to term. So you look at the function, you go, all right, are there any sign changes, meaning from positive to negative or vice versa? Well, this is a positive term, positive 2x to the 5th. This is also positive, so no change from here to here. This is also positive, no change from here to here. But there is a change in sign from this positive term to this negative term, so that's 1 change in sign. And then from here to here, there's no change in sign. But from here to here, you go from negative to positive, so there's 2 sign changes. And that means, according to Descartes' rule of signs, that there are up to, not definitely 2, but up to 2 real positive roots. Okay? What I'm going to do is just write 2 pos because I don't want to have to write all this out. So 2 positives, okay, up to 2. Now, what about the negatives? How do you know how many negative roots you have? Well, to figure out how many negative roots you have, there's a nice little trick here. We're just going to change all of the x's here to negative x. So we're going to be looking for g of, instead of x, the x becomes negative, this becomes negative x. Okay? And what happens is when you make all of these negative x, right, what's going to happen is the even-powered terms are not going to change because the negative gets canceled out by the even power, but all of the odd-powered terms will flip their sign. So rather than go into that in too much detail, I'm just going to flip the sign on all of the odd-powered terms. So this is a 5th power. That's an odd power. Instead of 2x to the 5th, it becomes negative 2x to the 5th. This is an even-powered term, so it stays the same. It doesn't change. Nothing changes. This is an odd-powered term, 3rd power, so change the sign from positive to negative. This is an even-powered term, so leave it as negative 4x to the 2nd. This is an odd power, because this is a power of 1. So this is used to be negative x, now becomes positive x. Okay. So when I'm saying change the sign, I don't mean make it negative. I mean, if it's negative, make it positive. If it's positive, make it negative. And finally, you get to this last term here. Technically, this is x to the 0, and 0 is an even number, so it's not going to change. But also, there's just no x to worry about, so you're not going to change the sign. There's no x to change into negative x, so just plus 9 stays the same. And now that you've flipped the signs on all the odd powered terms, right? Now you can do Descartes again. And this time you'll get the number of negative roots. So here's a negative term. From here to here, there is a sign change. So that's 1. And then from here to here, you're going positive to negative. There's another sign change. So that's 2. From here to here, no sign change. From here to here, yes, sign change. Negative to positive. And then it stays positive after that. So there were 3 sign changes. That means there are 3 real negative roots possible. Okay? Now, the fundamental theorem tells us that this is a 5th power function. These should add up to 5, and they do. So, that's not the answer we're looking for in its entirety, though. That's part of the answer. What it says here is state the number of possible. What are the possibilities? Possible positive and negative roots of the function. So, one possibility is that everything is real. They're all real. All 5 roots are real. Remember before I said it could be 5 real and 0 imaginary? Well, let's say they're all real. Now we know that 2 of them are positive. So we have 2 positive real roots, 3 negative real roots. And since this whole row has to add up to 0, this has to be 0 complex or imaginary roots. You know what? I'm just going to write imaginary. Even though technically complex is probably more to the point. So actually, no. Imaginary works actually. All right. So anyway, 2 plus 3 plus 0, that's 5. But what other possibilities are there? Well, if you just look at the positive ones here, what if the positive ones are actually not real, but they're imaginary? So you can subtract 2. You can't subtract 1. Once again, the imaginary roots have to come in pairs. So if these 2 positive roots are actually not real, but imaginary, that means you would have 0 positive roots. And then this imaginary will become 2. And we haven't touched the negative. Leave the negative alone for now. And that's another possibility. Okay, so we have 2 possibilities for what this could be. But wait, what if we went back to having 2 positive roots, but now the negative roots weren't all real? Let's say 2 of them were imaginary, because once again, it has to be 2. It can't be 1. So that would make this 1 negative root. And now how many imaginaries would I have? I would have to have 2 imaginaries. 2 that came from the negatives this time. And once again, 2 plus 3 plus 0 equals 5. 0 plus 3 plus 2 equals 5. 2 plus 1 plus 2 equals 5. They all have to equal 5 for this to make sense. There's one more possibility, which is if you had no positive roots because they're all imaginary, and only 1 negative root because 2 of them are imaginary, and then you had 4 imaginaries. That's the last possibility. And this is the answer you're looking for. Okay, and this is what you have to do on the homework tonight. I think in the homework they do this thing where in the answer key for the homework. So when you look at the homework help tomorrow, and you look at the answer key, what they do is they say something like, okay, the positive roots could be either 2 or 0. Then they put a semicolon between the answers. And the negative roots could be 3 or 1. They put another semicolon. And the imaginaries could be 0 or 2 or 4. I don't want you to write it this way for me. I would like you to write it the way I've written up here. It makes a lot more sense. But when you're checking your answer tomorrow, if you see this, it means the same thing. So just so you can understand what you're reading. Okay, how about this next one here? Let's do Descartes again. No sign change from here to here. No sign change from here to here. 1 sign change from here to here. No sign change and 1 sign change. So 2 positive real roots. Now, what about the negatives? For the negatives, we find g of negative x. Okay? Which means that for the odd-powered terms only, change a sign from whatever it is to the opposite sign. So this is positive 2x to the 7th. We're going to put in negative 2x to the 7th. This is an even powered function, a term, so leave it alone. This is odd power, change a sign. This is even power, leave it alone. This is odd power, change a sign. It's negative, we're going to make it positive now. And this one is even powered, so leave it alone. Wrong color. Okay, plus 9x squared. And now that we've flipped all the signs on the odd powers, we can do our Descartes again. This is a negative going to a positive, that's one sign change. This is a positive going to a negative, that's another sign change. This is the same, so no sign change there. From negative to positive, another sign change, and that's it. So 3 negatives, okay? But this is a 7th power function. Shouldn't 2 plus 3 add up to 7? Okay, so there's a problem there. It's supposed to add up to the degree of the function. The fundamental theorem of algebra says there has to be a relationship, or rather a matching, between the degree of the function and the total number of roots. So 2 are positive, 3 are negative. There's 2 missing roots that we're not accounting for here. All right, and here's the deal with this. If you look closely, this thing has a GCF. Yep, the old GCF coming back at you. And if you factor out the GCF, what is the GCF? It's x squared. All right, so this is actually x squared times, and then you have all this other stuff here, which is 2x to the 5th plus x to the 4th plus 3x to the 3rd minus 4x squared minus x plus 9. And here you can see you get all the same sign changes, because I didn't change the signs or anything. All I did was take out the x squared. So this is going to give you the same 2 positive and 3 negative when you do Descartes on this. But what happens when you have this? This root here, what is that going to be? That's going to be x equals 0. And 0 isn't positive and 0 isn't negative. The definition of the definition of positive is greater than 0, and the definition of negative is less than 0. So 0 is neither. 0 is neutral. And that's the reason why, and there's a multiplicity of 2 here, it's x squared. So what we actually have here is 2 factors, 2 roots, x minus 0, right? 2 0 roots. So we have 2 positive, 3 negative, and 2 0 roots. And now it's 7. Okay? So let's come over here and, write this out. So we have 2 positive, 3 negative, just like last time, but we also have 2 0 roots. And this means no imaginaries, because this already adds up to 7. The another possibility is if these are imaginary, so 0 positive, leave everything else the same now, but now the 2 that you took away from here, you can add on to the imaginaries here. Okay, that's another possibility. We can put back the 2 here, and now we can take away 2 from the negatives here. So we have 1 negative, 2 0, and now we have 2 imaginary. That's 2 plus 1 is 3. That's still 7. The other possibility is that we could put back the 0 here and still have the 1 negative and the 2 zeros. And this is 4 imaginary now. Okay. Okay, let's go on to this next part here. Writing polynomials if you're given the roots. We have done a little bit of this before. We're just going to do a quick run through of this with imaginary numbers now. So just to review what we should know from before. If I tell you that a function has the roots, the x-intercepts, -2, 0, and +2. These are the zeros, the roots, the x-intercepts. You should be able to realize that these all come from factors. And the factors are all in the form x minus a number, x minus c. So what factors gave you these 3 answers? Well, if you think about it, if you have a function, right, they gave you 3 roots, it's because you had 3 factors and you set those factors equal to 0 with the 0 product rule, because this, you made this 0, you made the y 0, and you solved x minus c, x minus d, and x minus e like that, and you got your answers from that. So the question here is, what are the factors? And once again, the answer is x minus the number. C is these numbers here. So you start off by just writing f of x equals, or y equals. And then for each one of these numbers, you're going to write x minus, x minus, x minus, and plug in the numbers. So what are the numbers? We got -2, we got 0, and we got +2. And now we'll simplify. X minus negative, double negative means a plus, so this is x plus 2. This is x minus 0, so it's just x. There's no reason to write -0, so just an x. But instead of putting it in the middle like that, which will look weird, I'm going to put it in the front like that. And then you got x minus 2 here. Okay, so this is the function written in factored form or fully factored form. But they want it in standard form. They don't want it in factored form, which means we have to multiply this out. So let's go ahead and multiply this out. Now when you have 3 things, you can only multiply 2 at a time. You can't multiply all 3 things at once. So either you can multiply, let's say, the first 2 here, or I think there's a little bit of a shortcut here. These 2 are conjugates. You see this? X plus 2, x minus 2, those are conjugates. And if you have conjugates, they multiply faster. You don't have to do the full first, outside, inside, last thing. With conjugates, you just have to do first times first and last times last, because the middle terms all cancel out. So let's just do that. It's a shortcut. What do you get if you multiply these 2 conjugates? X times x is x squared, and 2 times -2 is -4. And this should make sense to you because this is a difference of squares. And when you factor the difference of squares, don't you get that? Right? When you factor x squared minus 4, don't you get x plus 2, x minus 2? So hopefully that makes some sense to you. And then you still have that x over here. So here we go. Distribute the x now. X cubed minus 4x, and we are done. So this is the polynomial. They call this the polynomial of least degree with integer coefficients. Okay, it's a lot of fancy words in the homework. I copied that from the textbook just so you can see what the homework assignment looks like. They're just saying write the function. Don't worry about all that other mumbo jumbo. Integer coefficients just means that these are all whole numbers, no decimals, no fractions. And least degree means there's no multiplicity. There's no, like, you know, extra terms. So, and you're not going to create extra terms. Why would you do that to yourself? So there you go. That's it right there. So this is something we already kind of know how to do, but now we're going to do something a little bit different, which is what if they give you an imaginary root? Complex, a plus bi. Write a polynomial function in standard form, meaning not factored form, that has the 0, 5 minus I. Well, here's the thing. Imaginary roots come in pairs. I said it before. They come in pairs. You can't have a single one. So there must be another one. Well, if you have an a plus bi, you better also have an a minus bi, the conjugate. They're called complex conjugates. They always travel together. So if they give you in a problem any imaginary or complex, whatever, something with an I, you have to write another one. So there's this and, okay, and, I'm going to literally write the word and there. X equals, and then what's the conjugate of 5 plus I? It's 5 minus, 5 minus I, it's 5 plus I. So here we go. Write your f of x, put your parentheses down, put your x minus, and now we're going to put this over here and this one over here. So we get 5 minus I and 5 plus I. Now here's the problem. You see how this is x minus 5 plus I? The way I've written it, it looks like I'm only subtracting the 5, but I'm adding the I. So to make sure I'm subtracting all of this red stuff here, I'm going to put parentheses around it. Without the parentheses, this is completely wrong. This is just goes off the rails in the wrong direction. You need the parentheses. They're absolutely necessary. They're not optional. So there you go. So now you've got the function done in factored form. The problem is they don't want factored form. They want standard form. So we have to multiply this out. So let's multiply it out. We're going to FOIL. So we'll distribute this x to both of these. And we'll distribute this negative 5 minus I thing to both of these. And we'll get our answer. Okay. So here we go. X times x, x squared. X times this thing in the parentheses just means put the x in front of the parentheses. So you get x times 5 plus I. And this is positive, and there's a negative in front of this one, so negative. Okay. Now we're going to do this times x. Well, once again, you're just going to put the x in front of the parentheses. This time 5 minus I, and this one's negative as well, so put a negative there. So we got 3 out of 4 done. And now we're going to multiply this times this. Well, these are conjugates, aren't they? 5 plus I times 5 minus I. And like I said before, I'll do this in the scrap area here. 5 minus I times 5 plus I. Since they're conjugates, you just multiply the first times the first and get 25. And the last times the last. Well, negative I times positive I is negative I squared. Hopefully you remember from imaginary numbers that I squared equals negative 1. That's the definition. So this means this is actually 25 minus negative 1, which means 25 plus 1, which is 26. So this is just simply plus 26. Now I did some scrap work, but I made sure to put it all the way in the margin here and not disturb my graded steps. Don't do your scrap work in the middle here because it's going to mess things up and lose you some points. All right, cost you points. So anyway, we keep going now. We'll distribute these and these. Let's see, negative x times 5 is negative 5x. Negative x times I, they're both letters, so put them alphabetically. It's going to be negative ix. Negative x times 5 again, negative 5x. Negative x times negative I is positive ix. I'm sorry, negative 5x and positive ix, and then plus 26. And if you look closely, this positive ix and this negative ix are the same but opposite signs, so they cancel out. And we're almost done here. This means we have x squared. You got two negative 5x's, so that's negative 10x. And you have this plus 26. And now you're done. That is the function whose, well, if you try to find the roots, they're going to be imaginary. They're not going to be real. And they're going to be 5 plus I, 5 minus I. Okay, or 5 plus minus I, 5 plus I. All right. Okay, this next one is going to be a big one, which would take a long time to multiply out. So I'm only going to stop. I'm only going to set it up and do it in factored form. Now the homework is going to ask you to do it in standard form. And I've picked ones that aren't too long. But for this one right here, I just want to show you a big one without having to do all of the multiplication. So let's just put this one, set this one up. So once again, you have f of x equals, you have 1, 2 real roots. So put your x minus. And then you have this one imaginary root, but you have to know that there's got to be, and it's actually the same imaginary root as last time, there's got to be a conjugate. So 5 minus I, there's got to be a 5 plus I. Okay? Imaginaries travel in pairs. They never, ever, ever are by themselves. They're never singles. They're always in pairs. So they're always even numbers. So you're going to have 2 more. Now what goes here? Negative 1. This one's 3. This one's 5 minus I. But once again, use parentheses. 5 minus I. And this one's 5 plus I. Now the only thing you really have to simplify here is this double negative here becomes a plus. See that? So I'm not going to recopy this whole thing just to do that. So I'll just use my eraser there and do that. And there you go. That's fully factored form. That's not going to be good enough for the homework tonight, but we're going to stop there for our purposes. Now if you want to see what this would look like if I did multiply it, okay, there's the fully factored form right there. And this is what it would look like if I went through the process of multiplying it all out. Okay, but we're not going to do it for that one because it's a little bit too time consuming. Okay, if you're in the academic class, you're done. If you're in the honors class, stick around for one more example, and then we'll call it a day here. So we have this last one here. Write a polynomial function in standard form with this 0 and this 0. The thing is, this 0 right here is imaginary. So that means you have to say and. Well, this is 1 plus 2i. We need 1 minus 2i, the conjugate. Okay, conjugates mean like partners. So they do not get separated, these two. All right. So we're going to have three terms. 1, 2, 3. X minus, x minus, x minus. All right. What do we put in here? Negative 4 for that one. 1 plus 2i in parentheses. Excuse me. And 1 minus 2i. For that one. So there's the fully factored form version of that. Let's simplify this a bit. This becomes x plus 4. And now for these, let's multiply these here. Okay, so we go to multiply this. We're going to distribute. Let me just get rid of that. We're going to distribute this x to there and there. And we're going to distribute this 1 plus 2i thingy there and there. So let's see what we get. We'll put a big set of parentheses here and here. And we'll put everything that we're going to do in here. So x times x is x squared. X times the parentheses here will just be the parentheses with an x in front of it, right? But don't forget there's a negative here. So negative x times 1 minus 2i, which is that times that. Okay, that takes care of the distributing of the x. Now we're going to distribute this parenthesis thing to both of these. So this thing times x with a negative in front of it is negative x times 1 plus 2i. And finally, actually make some room here. We're going to multiply this red thing times this red thing. They are conjugates. So how about we come over here in the scrap area, 1 plus 2i times 1 minus 2i, okay? And since they're conjugates, we can get away with just, we can do the full FOIL and things will cancel out, or you can just realize I can do first times first, 1 times 1, which is 1, and last times last. 2i times negative 2i is negative 4i squared. Now, since I squared is just a negative 1, this is 1 times 4 times negative 1. This is 1 minus negative 4, which is 1 plus 4, which is 5. So this whole thing is just a 5. Okay? So last thing we have to do here is distribute the x here and the x here. Okay, so far we're here. This is an x squared. Okay, what do we get here? Negative x times 1 is negative x. Negative x times negative 2i is positive 2ix. Negative x times 1 is negative x again. Negative x times 2i is negative 2ix. And then you get your 5 here. Well, this term and this term are exactly the same but opposite signs, so they cancel out. So what do I have now? X plus 4. This is x squared. I have a negative x, another negative x. So that's negative 2x, and I have a plus 5. Now the last thing to do is to multiply this times this, so you're going to have to distribute the x by all these and the 4 by all of these. Since we're running a little bit long on the time here, I'm just going to show you what happens when you do that. You get this polynomial up here, and that's going to be your final answer. Okay, well, see you at the next video.
Check this.